Okay.
Yep, all good, all good. It's
All
in play
right.
mode. Cool.
Okay. So, again, thanks, Chang. And the best thing you've done that you have not, kept on reading my bio. I mean, thank you very much. People can read it offline. So this morning, again, thanks for the people who showed up. I know it's very hard to do this on a Sunday morning. But I hope to keep this light and interesting, and take you through a very quick journey over the next, type of 45 minutes into this whole area of Edge AI and its growth, and then look at some mission critical, industrial applications in which Edge AI could play a role in empowering, in running more efficiently, and so on and so forth. So that's where I spend most of my time, like Dr. He mentioned. The Center for Distributed High Performance Computing at Sydney University. The center has a whole bunch of different type of activities. It's been around for the last 11 years, and we get funding from all sorts of type of government, industrial type of sources, and so on. Most recently, for the last kind of couple of years, and some of the work I'll be touching on in this presentation is covered by the Australia-China Center for Energy Informatics and Demand Response Technologies, which is a bilateral center funded by both the Australian and the Chinese governments to support research in energy informatics. Over the years, we've hosted many people, from all over the world, students, researchers, people coming to spend sabbaticals with us. So do feel free to reach out to me in case, hopefully, in a post-COVID-19 world, we could go back and try to host people and receive visitors. Okay, a bit of, kind of a quick background about edge computing, where it came from. So really, like any other technology, kind of, and we've seen this happen time and again, in which a technology comes about and people start talking about it as if it is something new or totally new that didn't exist before and started just to exist when people heard about it. And that's the case for many technologies in computing, where the history keeps repeating itself. And edge computing is no exception, where again, the basis of edge computing really kind of starts from the early 1990s. Again, as you're going to see, as we define edge in a nutshell, I'm going to touch on this again in another 1 or 2 slides, is in which you're trying to bring, certain capabilities closer to where the user is sitting, right? So whether you're doing compute, whether you're doing storage, whether you're doing, any type of, running applications of any sort, you're trying to improve the capabilities of the user to run these applications more efficiently. And of course, in this case, we've seen people do this in industry and academia from the early 1990s with Akamai content distribution networks. At the time, Akamai is still around with us as a company, introduced this notion of placing these local servers near where the consumers are, and placing in these local servers data that is needed by the user to drive their applications in a much more efficient way. So again, these were called, content distribution networks those days when it started, but really kind of, they do fulfill the same purpose. Of course, kind of we move on and we hit 1997, where this notion of pervasive computing started, and some of us probably do remember pervasive computing, because at the time it was really kind of a big wave that started many publications, many papers, even many journals that started to publish on the topic of pervasive computing. And I'm sure some of you must have heard about this and probably seen, even today, actually, we do hear every now and then about a paper on pervasive computing, or have a title of pervasive computing in the or the word or the keyword in the title. So, for example, the idea was simple. Again, you have these surrogates in which, kind of allows, kind of mobiles or mobile type of devices that have very kind of limited capabilities. And through the use of or being kind of in close proximity to these surrogates, you were able to do really kind of the compute intensive or data intensive type of operations, like for example, speech recognition and cyber foraging and so on. And all that, kind of allowed these mobile devices to have really kind of more, sophisticated capability. Of course, again, the wave continues, and then come 2001, we started again to hear about the next wave, which is really kind of peer-to-peer computing. And in this case, again, we've seen this kind of overlay peer-to-peer networks, being used to really kind of avoid, kind of long distance communication or long distance links, because again, the moment you move things over a long distance, the chances of failure become much higher. And of course, we all again know about peer-to-peer computing, and again, a lot of papers and products were again developed during that time. Of course, again, we move again. The wave keeps on moving, and then come 2006, we hit the revolution of cloud computing around 2006, 2007, around that time, in which again the whole idea of a cloud was basically to open up all these big data centers and allow really kind of people to buy time on as a pay as you go model, in which basically you have access to unlimited resources, again, and you pay for whatever you're going to use and so on. And of course, due to the nature of these big clouds, you have really kind of infinite type of access to compute resources, storage resources, and the like. And of course, we've seen that wave continue for many years, and still actually it's going on. And we've seen kind of change the face of the way we do computing today, and the kind of capabilities that are offered to users today. And of course, again, come 2009, we've seen one of the early papers that came about that kind of introduced the notion of a cloudlet, and this is basically what, in a nutshell, was the idea was, can we really bring cloud capabilities closer to where the users are sitting? And this means that, like, where the data is being generated or where the data is being used, and therefore, like, the user could be sitting anywhere in the world and still feel like they have access to the cloud or some form of cloud capability. And this was like, during, kind of 2008, 2009. And of course, in 2012, Cisco Systems came up with the term fog computing. And this idea was even to really take this idea of a cloudlet and even make it bigger, in which you put a lot of hardware in the in the fog. So the fog could contain compute, sensors, storage, anything. Any piece of hardware can go into the fog, and everything is basically surrounded by that fog, which means basically you're creating no distinction between the hardware, and people could basically run their applications in this fog or have access to capabilities that are present in this fog. And of course, from that time onward, we've seen, this whole emergence of a variety of technologies that basically aim to do the same thing. I mean, you hear the term, mobile edge computing, mobile cloud computing, cloudlets, fog computing. These all are similar technologies, mean the same thing. The fact that you're moving cloud capabilities closer to where the users are sitting, to allow the users to basically, have, kind of run sophisticated or complex applications, like the stuff they would, tend or normally you would expect to run inside the cloud and far away from the user. So in this case, we're bringing that capability closer to where the users are. So this is basically, kind of a very kind of small or short snapshot of the history of edge computing. So you can see now, edge did not just exist yesterday or happened 2 years ago, but it's been around, or the notion of edge has been around for a long time with us. And of course, as technology evolves, we see, also, kind of our understanding of that technology, the implementations, the way this technology is being, kind of used and being deployed also changes with time. Okay. Of course, like as I said, the edge is a new distributed computing paradigm, or maybe it's an old new distributed computing paradigm in which you're processing the data, like we said, closer to the edge of the network where data is being generated, again, to deal with issues like kind of latencies, fault tolerance, resiliency, and so on and so forth. And today, of course, as you can see from this figure, we can see this kind of a quick kind of snapshot of these technologies. And today, at the top of all of that, for example, you have IoT sitting as the biggest beneficiary of edge computing, and I'll touch on this basically a little bit, kind of briefly in the next 1 or 2 slides. So, IoT really kind of made edge more popular and more essential or important for the functioning of this big kind of vision of the Internet of Things. And today, of course, we see the Internet of Things being expanded into the Internet of Health Things, Internet of kind of vehicular things, etc., etc. So you can see there is so much variety in terms of the things that can be connected to the Internet, and therefore can be beneficiaries of edge computing. Today, I'll just talk about one style or one type or class of applications, and this is what's known as type of mission critical applications. And these are kind of very specific type of applications. They do exist in a variety of setups in our lives. Of course, you have also other what we call non-critical also or low priority type of applications, in which unstable performance can be tolerated, or low performance can be tolerated over a period of minutes, days, or even weeks, without having to really impact drastically on the environment. Mission critical applications don't adhere to this. I mean, mission critical applications are very sensitive, and they don't tolerate kind of low performance or kind of low latency. They just basically, the nature of these applications does not allow them to really kind of tolerate these type of failures. The whole application will fail. Of course, we could sit here and talk about this for the next couple of days. There's a whole variety of these applications with their own properties and characteristics that basically say, look, I mean, we have our own special needs, and these needs need to be, met to be able to really kind of run efficiently and run effectively and service the user. Some of these applications, of course, medical applications, of course, as the name implies, these have to deal with, like you're dealing here, especially with applications in which you're dealing, directly with patients' lives and well-being. You cannot really tolerate failures, and that's for obvious reasons. Other applications, and I'll touch on some of these applications, or at least 1 or 2 of these applications later on in my talk. You have also financial applications, in which again you're dealing with very kind of strict type of requirements, and that's again, there is a lot of type of money involved in these type of applications. You're managing, big funds. You're doing, type of stock market monitoring or analysis, and in this case, again, you cannot really tolerate these type of failures. Military applications, and as the name implies, just like medical applications, there is definitely the need for very specific type of real-time, type of needs, with safe operations, of these type of applications, with secure operations of these type of applications, and the defense world is full of these type of applications. Of course, industrial applications are many, going all the way from manufacturing to vehicular type of networks, in which you could be deploying some of these networks in industrial applications like mining sites or dangerous zones and the like. And again, these applications again cannot tolerate failures, because again, a failure of one component in the system could mean a cascading failure through the whole system, where different failures will start taking place, and for the whole system, or other systems connected to this system could collapse. And of course, another good example of this is, for example, the systems you'd expect to see on a plane, where again, failure cannot be tolerated, and of course, the failure of one element or one component could lead to the failure of the whole. Of course, some of these mission critical applications do have certain requirements, and again, the list can be very long. But again, if one is to extract kind of a half a dozen of these type of characteristics, you'll find that most of these mission critical applications have heterogeneous hardware, which means like they could be mixing a variety of different hardware type of architectures and so on, and different compute configurations as well. We have what's known as mixed criticality, which means like again, you're trying to mix different components in a system like that, or a system which is composed of systems. So some of them have real-time constraints, and some of them have non-real-time, for example, constraints, and so on. And you're trying to meet all of these constraints within the same type of framework. What's known also as multi-level security is crucial. Again, some of these systems cannot tolerate that, and like especially, for example, like we said, defense systems or health systems and the like. Safety certification. These systems also need to be certified, right, by a third party. Otherwise, you cannot really deploy a system like that you build into for example, into a war environment, or into the for example, intensive care unit of a hospital. You cannot put a system there that has not been properly safety certified or gone through some testing and obtain certifications for it to really kind of go into these type of mission critical setups. Flexibility, again, the system needs to be functional because it could be distributed across a whole environment, like multiple devices within the environment. Also needs to be within the flexibility type of element needs to be, the system needs to also be scalable, which means like you could basically grow the system or increase or add more components to it while the system is still going to be running gracefully and not degrading or not failing and so on. So that also kind of puts an added pressure on the expectations of these systems. And of course, communication means like we need to have enough secure and efficient and latency type of tolerant type of mechanisms within the system to allow its different components to communicate with themselves or with each other, or also communicate with the application or with the user on the other side. Okay, so you can see the moment you start thinking of mission critical, you can start seeing some of these elements become more important, as opposed to a system which is, for example, non-mission critical, where some of these issues don't arise, or even when they do arise, they are not really of importance or great importance, because they're not going to lead to a total failure of the system. Okay. So the question here is, do we really move all these applications to the cloud? Of course, if we do that, then we're solving all our problems. But of course, the moment you move the stuff into the cloud, you're going to deal with other issues, whether they're like laws of physics, because again, the moment you move things away too far from the user, you're going to start dealing with issues of again, latency. You're going to deal issues with, for example, internet service providers not delivering or giving you, like for example, a proper infrastructure, or the infrastructure is not very reliable or fault tolerant and so on. Because many users, or the majority of users are not sitting next door to a data center, right? I mean, they're all sitting far away from data centers. So moving everything into the cloud becomes really kind of not the most practical type of solution. And of course, apart from laws of physics and latencies and so on, we talk about the laws of the land, because in this case, if you move stuff into a data center which is sitting in a different country, then you need to deal with the laws and regulations of that country, so which is really different from where the user is sitting, for example. Of course, again, cost comes as an issue, because you need to pay for that infrastructure. And then the moment you move things far away from the user into the cloud, then you have to deal with issues of failures. I mean, that becomes inevitable, because again, you're too far. Say, for example, you're running operations in a mining site, and you're moving all the stuff you're doing, you're moving them into the cloud, or depending on the cloud, then it's inevitable that you would expect to see failures happening. That will happen, whether you like it or not. And then how do you deal with that? So all of that basically, and there are many other issues we could sit here and list, that makes it impossible for us, given the mission critical requirements that we've seen in the previous slide, kind of be fulfilled within the cloud environment. So basically that means that we need to come up with a solution that is a little bit more realistic, more practical for these type of mission critical application. I mean, say you have a computer on board of a vehicle or a car or whatever. You cannot really expect things to happen kind of very quickly when you're starting to move stuff between the car and the cloud directly. It just doesn't happen. I mean, there is latency and so on, and accidents could happen, and therefore again you will have type of a big failure in the system, and that's definitely one of these mission type of critical applications. So having to move the stuff or just work with the cloud directly is definitely not the most practical solution for our needs or for the needs of mission critical applications. Of course, in this case, edge comes to play a role here, and like we said, so in this case, basically you're moving the stuff closer, to you're moving some compute, some storage, some kind of sophisticated ability or capabilities closer to the edge of the network, closer where the data is being generated or being used by users, for example, the edge of the network. And of course that allows us to do a variety of things. Of course, that also deals with the issue of speed and latency, because you can do fast responses. You can respond very quickly to, for example, things that happen. Also, that allows you to do cost savings, because again, you're putting the stuff closer to the user, where you're not really kind of using the bandwidth, kind of more frequently, and then wasting the use, of that limited bandwidth as well. And of course, security becomes a big problem, because again, you're keeping the data as you see here, as I say, as you go closer to the data center or the cloud data center, some of the privacy and security issues become more serious, because again, you're moving the data away from where the user is sitting, right? So in this case, security becomes an issue, because the user could say, look, I mean, I don't feel comfortable with moving all of my data to the cloud data center. I need to keep some of this data close to me and so on, especially if this is like financial data or health data and the like. Of course, scalability is also a big issue here, because the users these days own multiple devices, and these devices could be sharing the same data, or at least parts of the same data, what's known as model sharing or data sharing. So in this case, when you have these devices closer to the user, you need these devices to be closer to the user, or their content to be closer to the users. Then scalability becomes much more flexible, or much more easier to implement, because again, most of these devices will be sharing. It's inevitable that they will be sharing some data and so on, because they belong to the same to the same user. And of course, they could be doing the same type of computation. For example, you could be doing video streaming on an iPad, on a laptop, or even on your TV, using your internet box, and of course they all belong to the same user. So it's inevitable that they do the same thing for the same user at different times and so on. And of course, there is greater reliability, because even if your connection to the cloud fails, you'll still be able to really run stuff in a much more closer to you. You're getting cloud capabilities closer to you. So in this case, you could pretend as if it were you're having your own cloud, which is your edge. And then when the restoration, or when the connection to the cloud gets restored, things can be updated back into in the cloud. And during all that time in which the connection was down with the cloud, you are still being able to really kind of run your own thing, do your own thing, as if it were nothing has changed. So all of these things are all pluses, really. These are all kind of plus points in terms of what edge can bring to the game. And in this case, you can see it brings a lot of good things that allows us to operate in a much more kind of flexible manner and so on. And of course, all of these things also, you can see all these pluses also are very important to run type of mission critical type of applications, because they do tick all the boxes, or they fulfill all the needs of mission critical applications. So the question here is, where is the edge? Where does the edge sit, right? Because in this case, I showed you like a 3-tier system in which you have the user, or or where data is being used and manipulated, and then you have an edge in between the cloud and the user. But of course, today, this is very sophisticated, and the edge could be sitting, kind of anywhere in that spectrum, all the way between the cloud data center, all the way to, to the end devices, or this could be Internet of Things type of, devices and so on, or generally what's known as smart things. But in between, you could have edge or edges owned by a variety of providers. So in this case, for example, you could have, for example, the appliance vendors could have their own, edge devices. You could have the network vendors, could have their routers and gateways to be part of the edge that is owned by that vendor. And of course, the service providers could have their own, edges. So now all these type of hardware that existed before, like the cell towers, the routers, the gateways, the appliances themselves, now become more sophisticated as the technology moves, as the design of these devices becomes more sophisticated. These devices themselves could become edges, but owned by a variety of different type of providers. And of course, in this case, you also have, the service providers could have even multiple edges, right? So an edge here in this case is not just a single tier or a single level edge, but it could be multiple tier edge owned by the same vendor. So in this case, for example, you have a service provider that owns like a regional data center, as well as the edge, which is really the hardware sitting inside the cell tower. So you can see the edges also could be defined in a very flexible way, or a very flexible manner, and it could be sitting in a variety of locations. Again, mission critical applications. Let's kind of visit a couple of these applications, or a few of these applications, and see what does that entail, what does that mean for us. So again, in this case, I'm going to restrict myself to, again, to two classes of these applications, maybe, two classes and a bit, because again, we could sit here and talk about these applications, and there are many of those, and I'm sure some of our, listeners today in the audience would know, kind of some of these applications, or have their own applications that fall under this type of banner. All right. So in the medical area, we've been seeing, a flood. Of course, the idea of introducing, automated or computing or IT in general into healthcare system has been going on for decades now. And that also kind of, it's part and parcel of a variety of these systems in hospitals and clinics, and in different type of, different health type of providers. We've seen, like, maybe even 20 years ago, people started talking about the smart hospital, especially during the wave of like, again, pervasive computing or peer-to-peer and the smart, devices, kind of sensor networks and the like. When they started appearing, people started at the time talking about these smart hospitals, and many even industry providers, big players in the market, started delivering or building hardware for, kind of smart hospitals and the like. And of course, part of these systems, of course, some of them are non-mission critical, but also others are also mission critical application, which require, kind of real-time functionality. And of course, they cannot tolerate, kind of, long latencies when you're trying to, for example, deliver a service, especially if this unit is deployed, closer to where the patient is, especially if it's, like I said, an ICU type of environment, kind of intensive care unit and the like, then there is definitely no room for mistakes in this case. One case in which we dealt with in our work was basically during 2019, actually, 2020, we began working with our colleagues in Wuhan, at Tongji Hospital in Wuhan, and at the time, this is really kind of where the whole, COVID-19 wave started, and these guys were literally struggling, and actually at the time we were very fortunate because we applied for a medical type of application with our colleagues at Wuhan at HUST, Huazhong University of Science and Technology and Tongji Hospital, but that was for a different type of application at the time. So it was like, something to do with monitoring, type of fetuses and pregnancies and so on, and in real time in non-invasive ways. But we won the grant, and suddenly, we had this, kind of COVID-19 thing starting, and our colleagues said, can we really shift our attention to this, because this is now becoming much more important. And the idea was, can we really help our colleagues in which they had data for more than 2,000 patients. Of course, access to the data is very restricted, because again, you're dealing with health data. And the idea was, can we really build a system in which it combines edge and lightweight machine learning to allow us to really tell our colleagues that a certain patient is going to go into the ICU over the next 24 hours. This is known as forward triaging, which means like you're allowing the doctors in the field to do better planning for patients. So when you say, look, patient X is going to go or is going to need ICU service over the next 24 hours, then they can prepare the bed, the equipment, whatever. And the doctors actually, in this case, they don't even need more than 24 hours of kind of lead time to allow them to prepare these facilities for these patients. And the idea was, can we use the data for patients existing in the system, and then looking at also other type of information for these patients, like blood tests, X-ray tests, and so on, and then bring all of that to see which patient is going to go into a state in which they're going to need an ICU, or which patient case is stable, etc., and they can be treated outside the ICU. So the idea was, and this whole thing sits under this whole banner of what's known as the P4 medicine, where we're doing predictive, preventative, and personalized and participatory. Participatory means in which you're basically, each patient's data is used to provide something very specific for that patient. And the idea was really kind of dealing with, or the challenge here. By the way, in my presentation, I show or refer to papers that are either going to appear or appeared already, and in case someone wants to basically refer to this work that I'm talking about specifically. So you'll see these as text in blue in my presentation. So the idea here was to, again, develop a system that allows you to basically collect the data and collect the lab tests, collect other information that the doctors basically kind of bring or basically kind of feel it's important to them, and then provide an early warning. We're saying like, so and so patient will have deterioration of their health, blah blah blah. So you need to really kind of prepare an ICU bed for them, and so on. And of course, in this case, I mean, the outcomes really kind of exceeded our expectations, because again, the data is collected by different doctors, especially if the data is basically what's known as data, like, where doctors collect this data when they're going or doing their rounds on patients. So in this case, some of this data collected by different doctors could have different formats, could have gaps in it. Like, a doctor, for example, might not show up today to do the walk, and then therefore there is a gap in the data. So here we're talking about, data for more than 2,000 patients, but the data was not really very clean. The data had gaps in it, and so on. And the idea was, can we use this information when you're collecting this data? And by the way, all this data, all this computation was happening inside the hospital. So none of that data got leaked outside the hospital for privacy reasons. And basically, we had a team member from the research team went into the hospital, stayed in the hospital, and was doing all that compute inside the hospital and providing the advice to the doctors from hardware which is sitting inside the hospital. So for 1 day ahead predictions, our model kind of achieves close to basically, a 90% of success for again saying which patient is going to deteriorate. And of course, keep in mind, this is data which is not clean. It's not really kind of formatted to our liking, or all the data gaps are being filled, etc. No, this is data from the field in which we get provided this data. The data gets updated on daily basis, with new information for patients, new lab tests, new other type of information, and the idea was, kind of go back to the doctor saying, we think this patient is going to need an ICU, type of care in the next 24 hours. Of course, one of the biggest problems in this case was the fact that when we looked at this, we could see that there are about 250 features that needs to be fed into the learning model, and that is of course not very practical, because having to have 250 inputs into a neural network or the like, it's not very practical, and that will take forever, especially if you're trying to do the computation in very lightweight type of devices, because again, you're trying to do everything, like we said, inside the hospital, on hardware which is inside the hospital. So the idea was, can we really basically use again techniques, from the whole area of this explainable AI, and basically, we ended up taking all these 200. Again, the details are in the paper. 250 features. We were able to squeeze them down to really 20 most important features that were really influencing the output of these learning modules. And this is again, here we're just like we're demonstrating in the figures here, the use of so-called SHAP, or shapely additive explanations. And this is basically means what? Means like, you think of your neural network as a box. You're having your 20 top important features as input, and then the output is saying like whether this patient is going to go into ICU or not. But at the same time, the doctors themselves, they needed to know why we're getting this outcome. So the idea was, you cannot just give them a black box and saying that's what's going to happen, and we're not really sure because it's a black box, right? So the idea was to use explainable AI, in which we interpret why a certain output was appearing the way it appears, or why a certain value was appearing in the way it was appearing, and saying which of these 20 features is the most contributing factors to this output, and therefore the doctors could easily link this to their own readings, to their own, for example, inspections of the patient, and could say, aha, that makes sense, or that does not make sense, right? Because again, here we're using the doctors in the loop, because that's important for us, because we're not doctors. We're just taking data and running stuff on using machine learning, or lightweight machine learning in this case. And the idea was, we needed to go back to the doctors and convince them of the outcomes we were getting. And that was really kind of a very interesting type of case. And of course, even today, we still have other projects with the same team, because again, that was really kind of a very kind of effective, I would say, and very successful type of projects in which we work together like one team. And of course, in this case, again, these are some more results from the papers, in which basically, kind of, you're looking at two different patients in this case, giving, one day, to the actual diagnosis. And then, of course, you'll find like one of them is going to go into ICU, the other is not going to go into the ICU, and so on. And of course, we're able to do this, for a whole range of these patients. The other case is also from within the same environment. In this case, was to look at what's known as so here we're trying to interpret why or kind of predict kind of why sepsis happens. So sepsis happens basically when the basically kind of today, after COVID-19, many of us have heard of the term sepsis, because it's also part of COVID-19 when basically the patient's organs start basically dysfunctioning or shutting down because again of the virus, and this can also be bacterial, not necessarily viral, or also fungal. We've heard about the black fungus, which is basically affecting some of these patients. And of course, the moment type of sepsis sets in, then you end up with a variety of type of conditions. And again, we did some work on this in which we could predict whether type of sepsis will take place or not take place, and why it's taking place, and so on. some patients. Here we're just basically using lab indicators from the labs in the hospital, and we're basically able to really kind of help with again understanding better why kind of sepsis was happening. Again, more results again from this paper here, on these aspects, or some aspects of this. You can see again, there is a lot of need. I mean, COVID-19 showed us at least one aspect of a mission critical type of systems, and the need for these type of systems in the theater itself, in the hospital itself. And we looked at two cases in this case, predicting type of deterioration due to COVID-19, and also looking at sepsis data. But there is a whole range of other things one could look at. And of course, if you take COVID out, I mean, you look at other conditions, there is definitely more room, more opportunities for more type of kind of mission critical type of applications that do run in these environments. And of course, the more data you have, or the better capability you have to manipulate this data, work with this data, because again, the data is noisy, the data has gaps in it, and so on. The more you're in a position to provide, better, kind of predictive capabilities. Another class of applications away from health is the whole area of energy. And again, also for the last few decades, we've seen, kind of people pushing for greener energy and so on. Over the last, again, 10 years, we've seen the emergence of the so-called energy internet, and that basically meant bundling a range of ICT technologies, basically. And of course, that could be IoT today or edge today. But before that even was, the use of other type of IT technologies. And of course, like, AI and machine learning and so on, to basically look at how could we really kind of provide or deliver energy in a much more efficient manner, provide, kind of, real-time responses and so on and so forth. And of course, again, these energy applications are also very wide, and there is a whole variety of these type of applications. So the first case is what's known as non-intrusive load monitoring. So in this case, where you have, for example, these are like, again, it's a system which could be, again, closer to the user, where again you're monitoring things like ovens, refrigerators, stove burners, and the like, and you're collecting all this data, and then you're building a model, which is again showing how electricity is being used in a residential setup. And of course, you need to do this in a non-intrusive type of manner, because you don't want the user or the occupant of the house to feel like they need to interrupt their daily routine in order to be able to really use this technology. So the technology is in the back there, it's collecting the data, it's doing its own thing, while the user is going about living their own lives like the way they do. So in this case, data is being collected, and basically we're looking at, instead of looking at the household type of energy consumption, we're looking even now more specifically at specific type of appliances and the like, to provide really kind of a better energy consumption profile for these users. And in this case, of course, there is a variety of these type of approaches. Again, you can see, here there is like light GBM. It's a light form of machine learning type of component, as opposed to things like CNNs. Again, here where basically our approach basically performs domain adaption when transferring trained models from source to target domains, right? So basically the approach itself could be, again, when you're comparing it with again state-of-the-art type of approaches, it's much more accurate, again, because again here you're introducing new components in the system. Your edge is allowing you to run more sophisticated type of models on closer to where the data is being generated, and so on. And that, of course, also allows you some sort of or a form of security and privacy, because we're doing stuff closer to where the user is, and therefore the chances of their data leaking and being used by a third party becomes much harder. Of course, that topic has other elements to it, has other dimensions to it, And that could be also the topic of a different presentation, because then there you go into certain elements that are very specific to privacy preserving for this type of data. And like for example, things like using a variety of type of federated learning type of approaches to trying to really do kind of privacy preservation. So combining both of these two different type of approaches to do that. Another case is in which we basically the question was, if you're deploying an edge computing system in the field, can you really use solar energy to power that edge computing system? So this could be a system, for example, in a hostile area in which you do have sun, like that could be a mining site and so on. But you're far away from comfortable or easy ways by which you could plug in your system into the wall. So the idea was, can we use a PV operated a photovoltaic type of system. So let's call them just solar panels for simplicity. So basically solar panels being used to generate energy that can be used by the edge system. The idea here, of course, becomes more complicated because you need to understand, again, the moment you depend on solar energy, there are other elements, right? So here you need to really be able to predict, when it's going to be cloudy, when it's going to be sunny, when are you able to really do X, when you're able to do Y, and so on and so forth. So the idea was, can we really build a framework that kind of we fit into devices, edge devices that are very limited in computation and storage capabilities. And again, the details are in this paper, and we were able to build a system that allowed us to basically, again, using very lightweight machine learning, allows us to do, kind of decent type of weather prediction in which we could easily say, on which days we could basically depend on solar energy to generate enough power, because some of that power you could generate during the sunny periods, and you could store it in batteries in the field, and then you can use that during nighttime or whatever to basically power the system. And of course, again, we use a system. You can see again the performance. It's in terms of predictability. You can see it. It's all in the above 94%, 95%, 97% in terms of being able to really kind of provide very high predictability, given historical data, giving data you're collecting in the field, and then you're using these two pieces of information to be able to really say or provide better predictability. As well here, as well as we also managed to use, just like we use in the case of the health case, we used explainable AI, in which we are able to really kind of cut down the number of important features to do this prediction to a sensible number of features that we could feed into our model and get good predictability. Again, more information, the details are in the paper, and we could show that it is doable. You could use some of this stuff in the field and still be able to really kind of deliver high rate of accuracy and so on. The third case, again, it's again looking at energy management, again, under uncertainties. This means what? This means that you have your edge boxes, you have your household, and then you have a mix of different energy sources. You have your usual utility grid, or what's known as a brown energy, to also like the green energy type of sources, like using solar, using wind, using thermal, cleaner sources of energy. And the idea of, can we really use both sources and mix both sources in doing so in such a way that minimizes our reliance on brown energy or dirty energy, and at the same time, can we really do that in such a way that also minimizes the bills and financial burden for the user. And the idea was, again, to build a system like that, to reduce energy costs from the utility grid and increasing the renewable energy utilization, which meant hopefully that you're contributing again to lowering the CO2 type of footprint on the climate, as well as you're trying to also use that form of energy generation or usage, lowering, as a result, you're lowering the bills on the user. Of course, there are lots of issues in this case, and of course, one of the biggest issues is the fact that, again, renewable energy is very, intermittent, which means like, you cannot rely too much on it. take only solar, and again, we go into the same situation in which we're trying to predict when is the best time to draw, solar energy or to use solar energy as opposed to again, drawing electricity from the grid. Again, you need predictive capability. You need ability to be able to do that in a very efficient manner. Again, that this is still very much ongoing work, and again, up until like, I would say probably like, a couple of months ago, we were able to really kind of achieve about 81% cost reduction of the optimal solution. So, it's a decent type of, capability that's allowing us or delivering type of, kind of efficient solutions. In addition, we're able to basically shift the load from to off-peak periods effectively, which means basically you don't have these big spikes on the grid. So basically, not everybody at the same time trying to draw energy from the grid at the same time. By doing things a little bit more smarter, you can easily distribute the load on the grid or on the system as a whole in such a way that reduces these kind of big spikes in the system. Okay, I mean, just before I close, there is again other varieties of these type of systems, in which again here, like, you have a mining site, and of course you can see here we're using again a variety of components where you have, like, for example, UAVs, you have, for example, trucks, you have, for example, buildings. They're all wired or have wireless kind of connectivity, and then of course you have these mech servers in the middle, these kind of mobile edge computing servers and so on, and everything connects to some backend kind of controllers or even servers, where basically you have a variety of hardware that's trying to talk to each other. So this could be a factory setup, or it could be a mining setup, in which basically all these components need to work in a very kind of synchronized way. So at least data don't get lost, operations don't get affected, and of course here failures are also cannot be tolerated, because again you're dealing with a very volatile environment in which you have a lot of humans also working in this setup, and you don't want people to basically kind of get injured or get for example kind of accidents happening to them. Again, it's a different type of setup in which also you have what we call or what the conditions for a mission critical type of application also apply in this case. Finally, again, trying to leave some time for questions and answers. Again, I feel personally these edge for mission critical systems, they have certain type of appeal, where again, the edge becomes really kind of the natural partner in trying to really kind of drive or operate mission critical applications. And these have challenges as well, like we said. I mean, in general, edge computing does have its own challenges, and some of these, of course, apply in the case of mission critical and non-mission critical applications. An important aspect of that is like looking at how do we really kind of guarantee performance predictability. That's a big problem, because again, you're dealing with very heterogeneous hardware. You're dealing with systems that could operate in a variety of conditions. And the idea is like, can we really have some sort of predictability? So at least the user or the application developer knows what type of performance they should be expecting. Also, realistic performance metrics. What you have in the case of, say, for traditional like clouds or server farms, it does not apply directly or immediately to edge environments. Again, due to the nature of these edge environments. So we need new performance metrics to do that. Also, you need new optimization models, again, because here you're dealing, like we said before, a variety of type of resources, and also a variety of operating conditions. Like we said, you could be mixing critical versus non-critical type of elements within the same system, right? And of course, finally, last but not least, is trade-off frontiers. The idea is, can we really build these systems and make sure that the cost is not prohibitive, right? Because if this system is going to be built and be kind of replicated, you'll have multiple copies of this. Say, for example, you're operating in a hospital, and you want to have multiple copies of this system operating in different parts of the hospital. Then you need to make sure that the price or the cost is capped. It cannot be really kind of, you cannot spend $1 million to build an edge environment, right? It has to be, less expensive, and has to do its job properly, and of course it has to be deployable and so on and so forth in a very safe manner. So at the end, really, I feel that the future of these mission critical systems will have multiple dimensions. So AI is one, definitely. Machine learning is one. That's unavoidable. We also have, IoT, or things in general, not necessarily Internet of Things. Could be health things, could be, defense things, could be a variety of these type of devices, and of course, edge, plays an important role. So we have, again, the devices are important because IoT is helping us sense the world, make sense of the world, and so on. And then AI becomes very useful to make sense of the world, right? So IoT collects the data, machine learning AI makes sense of the data or help us think about the data. And finally, the edge will become the platform or the delivery model for all of these type of applications or all of these type of services, whether you're collecting the data, storing the data, filtering the data, cleaning up the data, and then you're trying to analyze the data through data analytics and a variety of different approaches. So we see this convergence or confluence of edge and machine learning and IoT, and all of that will be definitely creating a very interesting world in which all of these type of systems could be used to really kind of empower applications and allow a variety of applications, mission critical and non-mission critical type of applications, to basically prosper and to really service users. All right, thank you very much. I'm happy to take some questions now.
All right, thank you very much, Professor Zomaya. Right on time.
Thank you.
Yeah, it was very structured, your presentation, and very inspirational, because my understanding is that a lot of research has been completed from the theoretical perspective on edge computing, and you have done a series of work on building systems, analyzing systems at the edge. This is amazing.
Yeah, I mean, it's a lot of work, because in the past we used to get away, actually, when we did research on even on cloud. We could easily do, build a model and do analysis, and then you use some sort of simulation tool or whatever, and people will be happy with that. But today, because of the nature of edge computing and a variety of these devices, and some of them have very kind of accessible prices, it's very hard for us to really do simulations and publish out of that. Or even you want to do a patent or commercialize something and so on, or even like deploy a system for a client or an industry type of contract. It's very hard. So all our work these days, or at least most of, I would say 90% of our work, is really doing this end-to-end system development, in which you do from the theory all the way to the system, and then deploy and run in the field and so on. And that makes the work, of course, a little bit harder, because, again, when you do simulation, that's it. You can start write the paper or whatever once the simulation is done. But again, simulations live in an ideal world. No matter how sophisticated is the simulation environment, nothing replaces the deployment in the real world. Because actually, in many cases, when we deploy, at least an earlier version of the system in the field, we start finding bugs and problems and so on that the simulation will not allow us to find. Again, when you deploy the system, say in a harsh environment, a simulation cannot really provide you with the conditions for such an environment, to be able to really kind of find the bugs, the issues, why a system could fail in an environment like that. So, but that again makes things much more interesting, because we see that what we really kind of started with us as if you will as a baby now becomes an adult, in which you're deploying it in the field. So you go through all the cycle from a simple idea to building the model, even doing simulations, and then taking finally prototyping and then deploying in the field. It's much harder, but I think these days with this type of field, it's very hard to really not do that. It's just not acceptable anymore, at least for the conferences, or at least for the clients, or for especially for industry type of applications. You cannot deliver a simulation to an industry partner, right? So you have to deliver a system. Yeah, and I'm sure others are doing the same thing. So
I guess many of us do not have the luxury to build systems, and because it requires time, and truly a lot of time and effort and dedication.
It takes different skills as well. So you need a team in which you're also kind of have access to people who understand the hardware as well. So it's not it's really, this is where it's known as the it's hardware software design, right? So you're not just designing software, but it's both co-designing both elements, and you need people on so you also need, for someone to play with the hardware, they need to have certain skills and being able to put things together in a safe manner. I mean, that's very crucial, right? Because you're dealing now with hardware that could be a variety of hardware, going all the way, not only the edge or edge devices, but you could be, if this is deployed in a smart home environment, then you're dealing with power issues and serious power issues. Dealing with health, again, you're dealing with a health environment and so on. So it's not, that's why it takes a long time to finish like a single piece of work. It takes in many cases you have multiple failures as well on the journey, because the moment you go into a real system, you're bound to fail. It's very hard to get a prototype to function the way you want it to function in the first time. So it's going to be incremental, and you're going to have failures on the way, and it takes anything between 6 to 7 to 8 months sometimes to finish one piece of work or build a system.
All right. Thank you. Ladies and gentlemen, do you have any questions for Professor Zomaya? Okay.
All right. They can put it in the chat if they want to. So.
Yeah, definitely. I have one more question. Actually, I don't want to waste this opportunity.
No problem.
So
no problem.
Understand that the latency provided, the latency, low latency ensured by edge computing or edge servers definitely is a powerful tool for mission critical systems. But I couldn't stop but keep thinking that edge servers usually they are small in physical sizes, and they're constrained by their computing and storage capacities. So, which means that they may be easily overwhelmed by bursting in workloads or DDoS attacks. So if a mission critical system are managed and powered by edge servers, there's a risk. There's a risk that it will not be mission critical because the edge servers are overwhelmed. So is that going to be a concern?
That's why sometimes you need to build. That's why some of these systems need to be purpose built for certain applications. So, for example, if this is a system being deployed, say part of a defense type of thing, like that's going to be part of a tank or part of something like that, then it has to be purpose built for that environment, right? So that allows it to be isolated from certain type of attacks, whether they are denial of service, or even sometimes you could have EMC attacks, like electromagnetic waves being targeted at this equipment to basically shut down the equipment. So it has to be isolated or insulated in a certain way that allows this not to happen, right? And the same thing goes in a health environment. But also don't forget, I mean, the edge can be very, like we showed in one of the slides, could have multiple devices in that edge, and the edge could have multiple layers as well, right? So between you and the cloud, if you're going to have a cloud, you could have multiple edge layers in this case, and the sophistication of the hardware could vary from layer to layer. So in which you could bring in more sophisticated hardware into this ecosystem, and that allows you to deal with denial of service attacks or even run more sophisticated machine learning algorithms and the like. It all depends on the application itself and the requirements needed for each application.
Well, yeah, that makes sense. Thank you very much.